we're back with a green screen, clearing 60 frames per second, and we're ready to move on to Vertices. So let's do that. It's been a couple days since I recorded. I think I recorded on Monday or Tuesday, but had to figure out the whole uploading process is new. So let's jump into this. Let's get into some vertice drawing. We have our green screen, and now we have a window with clipping space from, like, this is the center of the screen, and then in each direction it's 1 unit. So it goes 1 unit up, 1 unit down, left, right, and so it's 0, 1 all the way around. Kind of like, you know, a unit circle or something like that, which is easy to work with in space. So let me close this. So let me close this. Let me open something that I drew up real quick. Oh yeah, this is our Mac. This is our beautiful Mac, and we have our screen. And you notice how I put the clip. It's what's called clipping space, 0 to 1, or 0, 1, 1, 0. You know, this is all math. This is all X, Y coordinates. There's a Z, but we're not going to worry about that. We're just going to worry about the two-dimensional drawings. And so if we wanted to draw vertices, we're going to want to draw triangles. And the reason we draw triangles is because it makes graphics look so much better. If I pull up this image right here that I found of this dolphin, you notice that every one of these shapes is a triangle, and that's because it helps conform to the shape of a dolphin really well. If you use square, it would look really blocky, whereas a triangle can cut in half and bend. Square just has to lay flat, and so you get a lot more definition with triangles. The more that technology advances in graphics processing, the more triangles / polygons can be drawn, the better the graphics. So if this, say this dolphin was made up of maybe, I don't know, 1,000 triangles, well, in 5 years it could be made up of 4 billion triangles. Yeah, okay, that's a huge number, but yeah, so basically we can just draw a lot of triangles, and the amount of triangles depends on the amount of quality. Side note, if you have a good texture, the texture can also act as some sort of a rounder. So if this looked kind of bumpy and had all these little like triangular bumps in it, if you had a good texture or like image to wrap this dolphin in, you can kind of eliminate some of that. So you might get these little straight lines, but it would look a lot cleaner. But we're not going to worry about that yet. We're drawing some vertices. Let's draw some triangles. Yeah, let's draw a triangle at least. Let's start with one triangle. So here's our screen, and I'm going to draw just the most basic of triangle. They call this the hello triangle right here. This is the triangle that we want to draw. Okay, ignore like the lines with the blue. We just want to draw this triangle. I could even set it white. I'm going to give it no clear color so that it's easier to figure out. 0 opacity. And we're just going to draw a purple triangle. Well, it'll be black, but so we're going to put this triangle right there, and the center of the triangle is going to be right there, and -1, 1, just like so. This is what we're going to do. So you'll notice that this triangle is made up of vertices, right? So this right here is a vertice. I'm sorry, I got to start using different colors. Blue. This is a vertice. This is a vertice. This is a vertice, or a vertex, vertex, vertex. And a vertex can be made up of a position, a color, like we went over when we were discussing, let me pull up this right here. When we were discussing the vertex to fragment function, so, you know, when we draw, let me get rid of this guy. When we go from the vertex to the fragment, you know, we can give it color, and then it would interpolate these colors and give you all these inner colors. So we can give it the position, we can give it color, and then it would interpolate. And yeah, but first things first, let's give it a position, draw it. Another thing we should note is that metal draws its triangles in counterclockwise fashion. So in our array of vertices, we're going to want to put them in counterclockwise order. I mean, so we're going to go this one, this one, this one. You can start from any vertex, but you'll want to go in the opposite direction. And there's always going to be an opposite direction. This triangle right here, if this vertex was way down here, you notice that a triangle can't actually intersect itself. So if this were to go right here, it's not going to make a weird looking triangle. It's just going to be another triangle. You know, triangles are one of the only shapes that can't intersect itself besides a line. So, I mean, unless there's theoretical, like weird stuff that I don't know about. But yeah, a triangle cannot intersect itself, and that's what's really nice about drawing with triangles. So, yeah, let's get to it. I think draws in counterclockwise fashion. Yeah. Okay. So, first thing we're going to need to do is, how I like to start it, is to create a new file called types. And what this types is going to do is give us the types that will be on both Swift and the GPU. So we know that we can duplicate. And I'll show you that in a second. First, let's import MetalKit. And then we're going to create a struct called Vertex. So this is going to be our object of Vertex that we can just keep reusing over and over and over again. Our Vertex will contain, like I said, it can have texture coordinates, position, color. All we need is position, because we know that the position of these vertices are going to be right here, here, and here. So we just need position for now, just to get this triangle on the screen. So we're just going to go var position, which is going to be a float 3 XYZ. And yeah, so that's all you need. Vertex position, float 3. And since we have MetalKit, we have float 3. Save that, put it up there. Now let's go to our renderer and use those. So we'll so something we should also note is that with I could even pull this up in Chrome with the so if I go to fundamental, and then I go to this resource buffer and textures, you can, and I'm doing this on purpose, the MTL buffer object, which is what we'll make, represents an allocation of memory that can contain any type of data. We can pass whatever the heck we want, which is awesome. We just have to format it and shove it inside this MTL buffer. So let's do that. Let's go shove some stuff into a buffer real quick. I also like to point out that we are I'll point that out in a little bit. We'll get back at it. So let's do this. So we're using the basic vertex, basic fragment. Yeah, so we're going to use our command encoder. Our command encoder is kind of what bundles it up. So if you think of all of our data and all of our stuff as a rubber band ball, well, like the force containing it, pulling it all together, that would be the command encoder. And then we're going to send that rubber band ball to the GPU, and then it's going to untangle it, and because we're going to tell it how to untangle it, and it's going to make it into whatever the hell you want to make with a rubber band ball. I don't know what you make. That was a really weird metaphor. So yeah, let's do that. The command encoder is what we're going to use to encode the data into the MTL buffer. First thing first, we're going to need a vertex buffer. So var vertex buffer as an MTL buffer. Like I said, this is an allocated space of memory that can contain any data type. And then we're going to need some data to shove into this vertex buffer. Okay, so the data that I'm talking about are the vertices. So we're going to create a method called build vertices. And we're going to pass the device just like before. And we're going to go down here. We're going to pass the device, make a variable, MTL device. Okay, so now we're going to pass it in. We're going to build these vertices, because we need vertices to put into the vertex buffer, because we need data to put into the vertex buffer to go to the GPU. So I'm going to make a variable called, well, I'm going to actually, yep, this is what I'm going to do. I'm going to create two things. I'm going to create one up here called Vertices, which is going to be a vertex array, right? We went over that. So now this vertices is what we're going to create. So vertices, this is how you do this. You go boom, boom. Now we're going to create an array of vertices in counterclockwise order. And so if I bring up my beautiful image, I call things beautiful a lot, but they're so gorgeous. Where'd you go? You're somewhere. you're right here. So if I bring up this guy, put him over here, put him right here. We have 0, 1, -1, 0 right here. So we need to plot him, him, him. And so that's what I'm going to do. And I'll just go, so I'll go vertex, position. We got to declare this stuff. Float 3. And I'm just going to put 0, 0, 0 there for now. Just to kind of, we don't need that one. Okay. So I'm going to put a comma. I'm going to copy that. I'm going to go like that and like that. I'm going to delete you. Okay, so now let's plot this thing. So we can put, so the very first one's going to be 0, 1. The second one is going to be the one down to the bottom left, which is going to be -1, -1. You guys know math, right? Everyone knows math. At least this plotting of points. This is going to be 1, -1. And look at that. We have our flipping triangle. That was easy. That's just one triangle. So we have a vertex with this one triangle. And we will want to put these vertices inside of this vertex buffer. So we're going to create a method called build buffers, because there's going to be multiple buffers that we're going to pass. We're going to pass, oh, by the way, we don't need to pass this here. We could just call build vertices. We don't use the device there. My bad. I just want to pass the device because it's exciting. No, it's just a habit. So right here, we're going to call this func build buffers. Do this. Whoa. I don't know if you saw that, but I just did like a divide sign. That was kind of a trip. Where the hell did I go? And right here, we're going to build the buffer. And the building of the buffer, I should probably put you right here. Building buffer is just one line for each, and it's going to be really easy. So we have our vertex buffer, so vertex buffer equals device, and since it's a parameter, we don't need to unwrap it because it knows it's going to be something, dot make buffer, and then you see we have different options. So if I go like this, you see we have these 3 different options. So we have, these are the 2 that we kind of want to focus on. This bytes no copy is where we don't make a copy, but that's about the only difference. These 2 are the ones that we'll want to keep in mind. So make buffer with bytes is going to be passing, like, I don't know, data. And I keep saying data. Data is like numbers and whatever the hell data we formatted together. We're going to pass it in as bytes, and then it will translate on the other side. And then we can pass in a length and just allocate memory space so we can put whatever the hell we want in there at any point. So that's there's 2 different ways to do that. This would probably be for like a lot of optimization, and this would be just for me being right now easy. So we're going to go vertices. So we're going to store the vertices in the buffer. The length is going to be memory layout, which in C is, if you do C or C++, it's size of, but Swift has its own, which is called memory layout. And I think that's like a newer thing. And then with structs, you usually do stride, the stride of it. And then we're going to multiply that by vertices.count because this is the length. And if we just did it 1, it'd just do 1 and not the rest of the vertices, and would only draw 1 vertex, which would equal no triangles. And then vertices.count. And then we're going to pass in the options just like so. And now we have our vertex buffer. Very easy. See how easy that was? Draw a flipping vertex buffer. So now all of this is being done. We're building our vertices, building our buffers. Here's our vertex, here's our vertices. Okay, simple. Now, all we have to do is a couple of lines right here. So, command encoder stuff. I'm going to add this line. Draw primitives. And what a primitive is like, so if you press the dot, you'll see this point, triangle, triangle strip, line. We're doing triangles. And what that means is it's not going to draw one triangle. What it means is the way it draws the primitives is going to be a triangle. So if we're passing in 3 different vertexes, this is 1, this is 2, this is 3, it can connect them into a triangle. If we only passed in 1 vertex, it wouldn't know what the hell the triangle is because there's no extra data after that first one. And so it's It's like, okay, I have a point. That's it. And if you wanted to draw points, you could use point. But we're drawing triangles, so for every triangle, we're going to need 3 vertices. And we have that. So we're going to do triangles. Vertex start is just going to be at 0. And then vertex count, well, we have that. Vertices.count. Boom. See that? So now that we're drawing our primitives, we can now set the bytes in the command encoder. So we can bunch everything together for the command encoder, and that's as easy as calling command encoder dot set vertex byte buffer. So we're setting a vertex buffer. Obviously it's called vertex buffer. The offset's going to be at 0. You could put it at like 0, then 1. So if we were storing it all on the same index or on the same vertex buffer, we can take half for one part of our, like one half of our data, and then the second part, we just have to do an offset of that data on that same buffer object. Hopefully that was a good explanation. I could draw it out. So say, I'll just do it real quick just to, so if we wanted to, like, just so you understand what this offset means, it means if you have this array of all this data, so say this represented like eye color, and then this half of the data represented, I don't know, fingernail length, right? So 0, 1, 0. So this is eyes. This is fingernails. Well, we can say, well, the offset would be, well, say this was like a, I don't know, float 3. It's not. Float 3. We can say that we store I here, and then we can also use that same vertex buffer and store at the offset of float 3 the fingernail length. You see? So that's what that offset kind of means on the same buffer. We're not going to do that right now. We're just going to use one buffer for one thing. So that's what we want to do. This at is kind of important. It's at what space are we putting this in? So in the shaders.metal, there's what's known as address space and buffer space. Well, there's address space, device space. There's all these different spaces, and then we use buffers to put them in there, or we use StageIn or other different types of stuff. I'm going too far ahead. Basically, you just have to know that. Just keep in mind this at, and I'll go back to it. So we're gonna put this at 0 first, right? Because 0 is where we put things. So we've set the vertex buffer, and now we're drawing primitives. We're done on this page. This is gonna draw some stuff for us. However, it's gonna send it to the GPU. The GPU won't know what the hell to draw because we haven't done it here in the shaders metal class. So I'm gonna make this full screen. I'm gonna divide this, put the, oh, sweet. If this page didn't come up directly for you, just go up to manual, and if this doesn't come up, just kind of, I don't know, click around a little bit. Sometimes it gets a little weird, but manual, once you can get it to this folder directory, you can just go to renderer like so, and then renderer will come up. So once renderer is up, I can show you that, show you what to do. So we have our vertex function. We want to put our vertexes on the screen, so this is what we're going to do it with. So we're going to take in const device, and this is device space. Since device space, so when you're passing in like a pointer or a reference, in this case we're going to be doing pointers to the data, because we're not doing per vertex, we're doing like as a group of vertex, and I'll get into that in a second. But we're going to want to use device space, and that's what this is. So you can say device, or you can say nothing at all. There's like texture, I think. There's a bunch of different ones, but we're going to just do const device, and then we're going to take in a float 3, which is what our position is, right? Yep. So our position is float 3, and then right here we're going to take in a pointer, like I said, of vertices, like kind of an array of vertices, like an array of data indices of vertices, and then we're going to put those at buffer 0. Okay, so listen up. Buffer 0, we declared that right here. If we were to put 1 right here, we would need to put 1 right here. You know, we're declaring it at buffer 1, buffer 2, buffer, etc. So we're going to put it at buffer 0, and keep in mind this is an array of vertices. like an array of data of vertices. And so we have to keep track of that, and what we're going to do that is we're going to use a Vertex ID, and the Vertex ID is going to get that vertex at that position of the vertice array. So because we're not doing per vertex, we're doing a group of vertices. And so this will be called Vertex ID, and then we're going to use this qualifier called Vertex _ ID, and you have to put this in this exact form because that's just the rules. If I actually opened it up on Chrome for us to look at, but if you kind of scroll down around this 52, page 52, 50, 40, where are you at? It has all of these different things. So the per vertex identifier, the base vertex value of one is specified. They have like these base instance. So if you're doing instances, if you're doing, which we'll get into, if you're doing, the position's really important. You got to keep track of the position, and like there's different times when you use the position. This describes a window relative to the coordinates. Like this tells it what the hell the position is. So these are all the qualifiers, and I'll just go through these sort of as I do this. I'm not going to go too in depth. You can read through this. Dude, it's so hard. It's so much to read through at first, but once you kind of just keep doing it, you get it. It starts clicking. You're like, oh, okay, I know what that means. Just keep it up. This is fun stuff. I promise. You're going to be doing crazy things in no time. So we're at zero right here, and we're still returning this float 4. We don't want to do that. We want to get the vertices. We want to return the vertices. Oh my God, vertices at Vertex ID 1. Okay, so let's describe how the hell this works real quick. This is a float 3. This is a 1. Now, if we go back to this exact thing here, and I type in, all right, I think I just scroll to the top. Hopefully, let me go to 0. Won't go to 0. All right, scrolling for a little while. I'm sorry if I do this. Nope. Some of the first things that are noted on here are these, and you'll see that these floats. So float 4 can be declared as like a float, float 2, float. Or float 4 could be a float 3 first and then a float. Like these fill in those positions. You can also do stuff like this where you say position.z equals this, or you can say position.xyz because it knows that it's a float 3 and you can do xyz in a float 3. And so these are kind of cool to read through. Just kind of quick ways to access different parts of a float. So we're going to return this right here. Instead of returning just a float 4 with 1, we're going to return the vertice at the Vertex ID that we declared in our Swift, in this renderer, in these vertices right here. So that's what this is doing, is getting that Vertex ID from this pointer. And if I run this right now, we should be golden, like Ponyboy, who stayed golden. And we get our triangle. Look at that, our beautiful white triangle. It's drawing a white triangle because of this 1. This is 1, 1, 1, 1. Float 4, 1 just fills in all of the spaces with 1. So we're drawing a white triangle because all of the color is just put to 1 on, yeah. So that's that. Let's move on. Let's instead of just returning a position, we can return data out of this thing. We don't just have to return one float 4. We can return whatever the hell we want as long as we tell it what the hell everything is. And so staying along with this, we can go struct vertex right there. And so we'll just copy the exact same thing that we did on the vertex. But in this case, we have to, well, let's call this a float 4 because this is what we're going to be outputting. You have to output a float 4 as a position. So if we go back to this, you'll notice that when we go to 53, hold on. All right, where are you? 53. And you go down to this position right there, float 4. Position has to be a float 4. And so that's okay. That's okay. Position. And then we'll have the color for this. We're just going to match exactly what we put in this types for this guy, except we're going to use a float 3 because we're going to convert it. Because position should be a float 3. My cat sneezed. Okay, so instead of returning a vertex or a float 4, we can return a vertex, right? We can return whatever the hell we want. Pretty freaking sweet, if you ask me. All right, and so we can say vertex v, and then we can say v dot position, because vertex v, this is position, this is what it's using, equals float 4, this stuff right here, and we can return v dot position. Okay, so this is exactly like returning this float 4. Obviously, we're just setting data, okay? But I'd like to point out that we're returning a vertex now, so we can only return the v. Now, if I press play, it's going to say, nope, you're wrong. Can't do that. You have an invalid return type of vertex. That's because this position needs to be marked with this qualifier. If I can find this. Needs this qualifier, because this describes the window relative coordinate for the fragment. So, like when I throw this vertex into the rasterizer, because that's the sequence in which it goes into the rasterizer and then it goes to the fragment function, it needs to know what the hell the position is. If I pass it color as a float 4 and position as a float 4, it could be either or. It could be color, it doesn't know. So you have to put this qualifier right here as position. And now it knows what the hell you're talking about when it goes out to the rasterizer and into this fragment function. So when I press play, it should succeed, and now that it knows what the position is, it'll be able to draw the vertices accordingly, just like so. See? Now, since we're doing this position, and I put color here. We didn't actually have color on here yet. I got just like kind of antsy, I guess it looks like. So we're gonna add color. Let's do some color, because color is where it starts to get like really like, oh shit, you can color stuff. All right, so color is a float 4, red, green, blue, alpha. And in the renderer, now this is gonna break, because since we didn't declare these colors in our types, we have to do it in the constructor. And when we do this, we now have to go comma color. It's the float 4, do that. And we could just pass in white and it would work. So if I go right here, copy that, put it right there. White would work, but white's no fun. We're not gonna do white, we're gonna do like random colors. Actually, let's do red, green, blue. R. Green. Make it look sort of nice, I guess. And you can make these whatever you want. You can even do like 0.5, but I'm not gonna. But you could. You could. All right. Sorry, it's taking a long time. And then we're gonna do blue. 0, 0, 0, 1. There we go. So, why is this different? I don't like it when they're different. You push back one. Kind of picky. These can't be negative. They have to be unsigned ints. So you know. It's from 0 to 1. Can't have a negative color. I mean, maybe you could. I don't know. Can you have a negative color? I'm not a physics major. Com-sci. So here we go. So vertex, vertex, vertex. Now we have colors, and we're passing in those colors automatically because we're passing in the vertex.stride right here. See that? So it doesn't matter. Anything we add there can be added. Now when we go back here to the shaders, we have color. Like, since we're passing color, we can get the color. If we were to try to get this before, it wouldn't have existed. It would break. It would say there's nothing there. But now we can access the color. So we can say v.color equals, well, we have vertices at Vertex ID.color. And since we're passing in all like that. Now, when I press play, okay, it's not going to work. It's not going to work. Well, it'll, oh, well, I suppose I should, maybe, what's wrong here? I jumped the gun again. Damn it. This is not a float 3 anymore. This is now a vertex. See that? And we're not going to be storing it in device space anymore because I don't want to, oh wait, well, yeah, let's store it in device space and see if that works. So now, if I press play, too few elements in vector display. Expected 4 have 2. So vertices, float 4. Oh, well, there's that. There. So v.position equals there. We got 2. Why do we have 2? Yeah, we're gonna take in the vertex. Let me see if this works. I think I have to store that in the, yeah. Yeah, you have to put in the device space or one of these little spaces. But this complains because v.position equals float for vertices at Vertex ID 1. Ah! Duh, it's a vertex. Position dot 1. It's not just a vertice data anymore, it's stats. So now it's gonna say, oh, I know what you're talking about. I think too many expected. Now we have 5. Okay, so this vertex, oh, yep, so we're taking in, remember it's a float 3. It's a float 3. So we have to take this, copy it, and we'll do a conversion. So this will be vertex in, this will be vertex out. So this is the vertex we get in, this is the vertex we get out. And we're gonna not just return a vertex, but we're gonna return a vertex out. But we're gonna get a vertex in. And remember, this is now, we're still doing, oh, give me 1 second. I will be right back. I gotta do something. Okay, I'm back. Here we go. So we have our position. We don't need it as a position when it comes in. We know it's a float 3. And so we're gonna just take in the float 3 position. We have to return it as a position, but we don't need to take it in its position. We'll declare it on the way out. And then the float 4 color. So now that we have vertex in, vertex out, we can return a vertex out. This will be a vertex out. And we'll call it v out. This will be v in. Vertices. We'll keep it as vertices. This will be v out. Dot position. Out dot color. And so now we have v out dot position equals this. V out dot color equals this. Should be good. Let's run. And this is now returning v, which is not a thing. Now that we're returning a vertex out into the rasterizer, which will then go to the fragment function, we should just get a white triangle. Perfect. Why is it white? Why in the world is there no color? Because we've only done the rasterizer. We haven't implemented our fragment function, which is right there. We haven't done him yet. Rasterizer, don't touch him. We need to make him draw color. So out of the fragment, or out of the rasterizer, will come this vertex out. So this will actually still be in the exact form of a vertex out. And we're going to call it v in. I know it's confusing. We're going to use the StageIn qualifier because StageIn represents per vertex. So it's going to do per vertex, not group of vertex. So we're going to do StageIn. And then StageIn, we don't actually have to keep it track of each vertice. We could even do, I think we can do buffer 0. And then I'll go over StageIn in the future. You know, you can use buffer 0, but I'm not going to do that. I'm going to just use StageIn because it's easier. I think maybe, actually, you know what, now I'm thinking vn.color. I'm going to build this. I'm going to see what happens. Now I'm kind of reluctant. I don't know. It should, maybe. Okay, it worked. It worked because coming out of the rasterizer, you can do, as long as we have a position and the color we're declaring here. Yep, that makes perfect sense. That makes sense. We can just do StageIn, vn.color, since this color is going out to the rasterizer, and then the rasterizer is figuring out what pixels to draw, like which one should what pixels that are attached to here, and what should their interpolation be in relationship to these pixels. And then it goes out to the rasterizer, comes into this fragment function, and then we just say, okay, whatever, you know, put the color here that we've decided. We can like say times 0.5, and it would be a little bit brighter in all the color. So here's where we would do all of our like our shadow stuff, and then our fragment function would times 0.5, so it went darker, right? So we would have to do like times 2.5 to make it brighter, because times 0.5 divided the color in half, which made it really dark. So this would make it super bright, you know. So we can do all of our calculations here if we wanted to on that. So we're not going to do that right now. What we are going to do, now that we have color and we have our freaking triangle, we're going to admire it for a second. We're just going to look at it in all of its glory. And we're also going to talk about not just triangles, but planes, and not an airplane, I mean a plane. So if I were to take this coaster and turn it like this and put like this pen on it, it is now a plane, right? It's something that lies, like an object that lies on a plane. A plane. So we have a plane. This is a circle, but we're going to make a square plane or a rectangular plane based on the window. And let's go over that. So let me check my time. 35 minutes. We're doing really good. So now we drew this triangle, which is kind of cool. But now we're going to do planes, or just square. I'll call it square. No, I'm going to call it plane. So we have this right here. I'm going to delete that. So we're going to go here and we're going to do so here's our plane. It's going to fill up the whole entire screen for now. And in the future, we'll rotate it, translate it, blah, blah, blah. But for now, we're just going to keep it on the screen. We're going to go here and we are going to put our triangle. You could do it like that. You could do it like this. I just prefer like this just because that's the way I do it. But keep in mind, we still have, so we'll have these vertices. So we'll have vertice right here. This is a vertex. So this is like V1. This one right here, V2. And then V3 will be the first triangle, right? Because we get that triangle on the top. We'll have a triangle. Remember I said everything's made of triangles, so we'll draw this triangle. And then we'll go V1 to V3 to V4. So we have V4. Nice, right? So basically, instead of drawing one triangle, we're going to draw two triangles. Now let's do that. So let's go to our renderer. Right here for vertices, we already have our first triangle. Let's make our second triangle. So this one's going to be our big triangle, but we're going to kind of redo it. And we're going to go there. I'm going to make you shrink. Come here. I'm going to go to this. Put you right here so you can see. And then I'm going to take this blue, get a line real quick. And I'm going to replace this line right here with blue so we know that it's blue. So triangle on top, triangle on bottom. We're going to do the triangle first on top. So that's going to be in the position of, I like to start with this one right here as long as it's counterclockwise. So this is V1, which is 1, 1. So we're going to do 1, 1. The next one will be negative 1, 1. The third one will be negative 1, negative 1, which is good. So right here we'll go vertex 1, V2, and I'm going to put V0, V1, and V2 because these are technically 0 indexed. So if I go back just real quick, just for clarification purposes, if I go like that, like this, and I go like that, 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 we're going to go V0, V1, V2, V3. Okay, so now that we have our vertices in 0 index order, we know that's V1, V0, V1, V2. Now we're going to do V0, V2, V3. So if we go V0, like so, and then we go V2, and then we're going to do V3, which doesn't exist yet, so we got to make it, which is 1, negative 1. 1, negative 1. It's nice. It's already there. And then we're going to change these colors just a little bit. So this will be like, I don't know, that. And we'll go like that. And then we'll go 1, 1 right here, just so there's different colors. Because you'll notice that there's two triangles. This looks good. This looks good. What's going on here? What are you doing? Like that. Isn't that how it's supposed to go? Yeah, what are you doing? No, that's right. Yeah, sorry. So now we have V0, V1, V2. We've already said that vertices.count is what's going to be attached. We have the vertex.stride times vertices.count, so everything should be fine. Now when we press play, we won't just see one triangle. We should see multiple triangles on the screen, filling up the whole screen. just like so. We have the triangle on top, triangle on bottom, and this is what they call a plane. Now what we could also do to kind of show you, make it a little bit, we can go var size, and then we can go float equals, and we'll go 0.5. We're gonna do half of this, we're gonna put this to half. See how this is 1, we're gonna go half, and it's gonna draw the vertice halfway to 1, because remember that was our clipping space, 0 to 1. I don't know if I mentioned that. Yes, I did. I had to have. We talked about clipping space. If we haven't, it's these boundaries, 0 to 1. The clipping space is 0 to 1. It clips everything in that boundary. And then once we start doing transformations, it'll be like 0 to 1 million, whatever. But it'll still be within that. And then this could be lit. So now that we have 0.5, it should only take up half the space that the other one did. So and that's only because it's drawing the vertex at 0.5. Yep, so now it's a little bit smaller. We have our clear space in the background. This is clearing 60 times per second. And we have this beautiful freaking plane. One thing we can do to just kind of verify if this was all the same color, which we could make it the same color. Let's just do this. So say this was float for 1 again, float for 1, and we were like, I can't see the vertices. Where the hell are they? Because everything's so similar in color. Let me see. So we have, oh yeah, this is a plane. I know it's a plane. I know it's made of 2 vertices, but I can't see them. Well, there's this cool little camera down here that will take a screenshot, capture the GPU. It'll give you this right here, which you can see the top triangle and the bottom triangle. And then if you go to this manual and go to all GPU objects, well, it gives you the texture. The texture is literally like that is the texture because it's all the same color. The color is the texture. And then it gives you this buffer that if I come out a little bit, it'll give you the color at that position too. But since the color at that position is those colors, I'm just returning 1 in the GPU manually. So here, let me stop it and then go to here. Let me actually return that color, and then we'll do it again. Oh man, that makes my computer so loud. I don't think you can hear it. You might be able to. So we got that, and now if I go press that camera again, you'll see that we have this data here. If I go to the manual, all GPU bound objects, and then we go to the buffer, you'll see it shows us the colors at which these buffers, what they represent. So that's a cool way it's like a debug tool, which will come in handy later on when we're trying to figure out what the hell is wrong going on here. But that's just something to kind of keep in mind. I'm going to go back to the normal view. I'm going to go back to our renderer class, and we're going to discuss something. So right now we're drawing 6 vertexes. All right, it consists of 4 vertexes with a float 3 and a float 4. If you look at this, and like notice that we have this vertex and this vertex twice. And if you look at this image of this dolphin, and you look at one vertice, this vertice right here is connected to this vertice, this vertice, this vertice, this vertice, this vertice, this vertice. That's 6 vertexes that this one is connected to. We would have to put freaking 6 vertexes for this one, and that's for all of these. What? No. The answer is no. We will not. We refuse. What we will do is create some sort of a dictionary, more so, or an indexed array. So what we're going to do is we're going to create the array of vertices, of all the vertices that exist on this dolphin, one time. Not multiple times, one time. And then what we'll do is we'll give it an indexed array to index whatever vertice I need to draw. So right here I need to draw this vertice, which is 10, and then right here will be 11, and then I need to go back to 10 because I went back up here and then went over here, so I need this one again. So I clicked on it. Oh boy, broke it. Yeah, and so this is a mesh of triangles, by the way. I don't think I mentioned that. So what we want to do is, instead of drawing these ones twice, what we want is just V0, V1, V2, V3 in one array. So we go here and just one array, so 0 through 3 just one time, and then we want to index it. So a good way to do that would just be to go var indices, and we'll create an indice of uint unsigned int 16s, and that's because it's not going to be signed. There's no negative index. There's never going to be a negative index, and 16 is plenty of data. We can do a uint 32 also, but we don't need that unless we're drawing really big things, because the indices won't go that high for a freaking like six vertexes, and so we can use a uint 16 for now. If that becomes a problem, we can always up it, but it's as easy as saying indices equals array, and then we'll look at this picture and we say, oh, we want 0, 1, 2. So we're going to go indice, we're going to do 0 first, then 1, then 2. And then for the second triangle, we're going to go 0, 2, 3. These can be in any order you want as long as they are counterclockwise. So we're going to go 0, 2, 3. So 0, 2, 3. That's it. So we now are our indexed array, and now we just need to set those. So instead of so we have, we're going to want to pass this to the GPU in a buffer, in an MTL buffer, because that's how we send things to the GPU. So right here, when we say build buffers, we're also going to need to create an index buffer. MTL buffer. Okay. And then right here, we're going to go index buffer, same exact way we did before. Equals, and I'm just going to copy this. Copy, paste, and then instead of using vertices, we're going to use indices. The length will be uint 16 instead of, and this will be size because we use size with primitive types, and we use stride for like structs. And yes, because this only covers one, this will cover multiple different data types. Yeah. So now we have our index buffer. Let's send it to the GPU using our command encoder. And instead of like setting an index buffer or anything like that, we can just delete this line. And instead of saying draw primitives, we're going to say command encoder dot draw indexed primitives. Same exact thing. I'm also going to go over something real quick. So draw index primitive. There's multiple. You're going to want just this index buffer offset one that it ends with. There's this instance count that's also really cool, but that's when we're drawing instances. And instances, just kind of a quick brief overview, and we'll get back into them later. But instances is when say I have this these vertices for this one plane, and it's made up of like 10 million vertices, like so many. Well, we can either create a copy and send every single copy, so all 10 million vertices times 50, if we want 50 of them, to the GPU, or we can send one copy, one instance of that 50,000 million vertices, send that to the GPU, and then just tell the GPU that they're instanced, and so use that same exact one over and over and over again, rather than creating multiple copies. And that's kind of what instances are, but we're not doing that right now. We're just sending all copies over there. And so this will be .triangle, same thing as before. Index count is going to be indices.count. The index type, well, if we put dot, you'll see uint 32 and 16, the only two options, and we're using uint 16. The buffer is going to be our index buffer that we created, and the offset is going to be 0. And that is how you draw index primitives. So let's press play, and we should get the same exact thing with 4 vertices declared rather than 6. And I know what you're probably thinking, broken. That's what you're thinking, because I did not do this right. Look at uint.size times vertices.count. Silly person. So there's 4, but there's only 3 or 6 indices. We were way out of bounds. Way out of bounds. So same thing. Now we're drawing with indices rather than vertices. One other thing that I want to point out is that I know you're probably thinking, well, yes, we have less of these, but we have 6 of these now. Like, we have more to keep track of than ever before. Well, no, not really, because if you look at this, this is a float 3. Floats are huge, by the way, because for precision on like decimals, these have to be big. I think they're like 32. They might be 32. I'd look at. I don't know. They might be 32 bits per float. I'm gonna look it up just because. Float size Swift. I guess it's all over the place, but actually, you know what I could do? I'm just gonna do this as a cheat. So, and in it, I'll just do Swift dot print, and then I'll do memory layout, and I could do this in probably a playground, but I'm not gonna. Memory layout of a float 3 dot size. So, and then I'll do this. So let's see what that outputs when I run it. Oh, expected expression. What did I mean? Oh, nah, I don't need that. What was I doing? What the heck? Module Swift has no number name print because it's a lowercase p. This is taking longer than I thought it was going to take. I just want to show you the size of a float 3, or even a float. So if this is 16, so a float 3 is 16. A uint. Unsigned, so I lied. It was 16, not 32. So sorry. Still big. We look at a unsigned int 16. It's 2. Look at that size. Okay, so it would take 8 of these little guys to make up just one of these, and we have a float 4 right here, right next to it, 32. So, or 24. 32, 24 probably. But yeah, so you can just totally see how memory gets wasted if you use these vertexes. And then we'll have normals and texture coordinates to pass into this vertex. And it's just crazy. So indices is definitely the way to go when it comes to storage space. Moving on. Now that we're doing indice drawing and we have a freaking square or plane on the screen, I think the best thing to do now, depending on our time, which is at 51, running good. I'm going to do like an hour and something, because uploading takes kind of a long time. I learned that the hard way. We're going to do what's called constants. Oh, constant. What the hell is a constant? You might think you know what a constant is, but do you know what a constant is? No, we're not going to do that. We're not moving anything yet, because there's one more thing that we want to do. If we go to our shaders.metal, we are having to keep track of this Vertex ID. I'm sick of it. Are you sick of it? I'm sick of it, because I know that there's a better way to do this. Instead of having to keep track of this Vertex ID and doing it on this group of vertices getting passed in, why not utilize the vertex function as a per vertex, which means every single time it'll call this one time per vertex. So this wouldn't be vertices, it would just be one vertex in, not multiple. This is going to take some work. So you use this device if you're using a pointer or a reference. Not doing that. Also, when we're not using that address space at any buffer, we're now going to use what's known as StageIn. StageIn is when you use per vertex, and that's mentioned in that in this. When you do StageIn qualifier, I don't know. Let me see if I can find it real quick. Hopefully, find stage underscore in. There's a bunch of them. Yeah, so you use this for per vertex inputs passes arguments. So per vertex, that's the key word. So we're going to use StageIn now. Instead, we won't use this silly little Vertex ID anymore, because that's ridiculous. And now we're taking in a VertexIn. That's cool. It can't be a const. It has to be a const still. That's fine. Everything's the same. We don't need to keep track of this Vertex ID anymore, because it's silly. We don't want it. We're going to do per vertex, and there's different reasons why to do this and why not to, but I'm not 100% on them, so I'm not going to go over them. But so now we have StageIn, VertexIn. Oh, it should work, right? Because we're using StageIn, we're just going to do it per vertex. Vertices is not. This is just VN now. Sorry. You're thinking, oh yeah, this should work. Oh, it's going to be just fine. Everyone's going to be okay and happy, and no one's going to freak out. Well, this is going to throw errors. Because this position now, look at, so when you use this StageIn has attributes. So the position must be marked with the attribute index. So use attribute, right? So now our guys need to have attributes. So this is attribute 0, attribute 1. 0, 1. So now we have 2 attributes. See that? And so when we use StageIn, we have to use attributes. Position stays the same because we're still going to output a position. Color doesn't need to be an attribute because it's just the VertexIn. And I am curious as to what the truck is. Oh, attribute 0. Spell something wrong? See, sometimes it's just, I mean, I don't even think we need this constant where we just do VertexIn, which is kind of cool, but what is this? Give me, what do you mean? Did I spell it wrong? Attribute 0? These had to be attributes. Yeah, so now you're like, oh yeah, it compiled. Now it's gonna be like, oh wait, oh shit, oh boom, kablooey. And then we look at the function, the error, and we go up and it's like, vertex function has input attributes, don't worry about that. But there's no vertex descriptor. You're doing per vertex. Like, you can't tell me it's a float 3 or whatever. Like, I don't know what the hell it is anymore. You're doing per vertex. I don't know what the hell a vertex is, to be honest. I mean, I know I've declared what a vertex is by this function, but realistically, I can't determine what this is at attributes. Like, this makes no sense to me because I don't know how to put the data together and send it through as a packet. So inside of our renderer, what we need to do now is go back, reevaluate our situation, and look at this picture. Again, back to this guy. So we have our render pipeline descriptor, and we have our vertex function and fragment function. But now that we're doing per vertex, we need to do a vertex layout. We need to tell it what the hell the one vertex is. So we need to put that guy into the render pipeline descriptor. So let's do that. We got to create this vertex layout, aka VertexDescriptor equals MTL vertex descriptor. Okay, we're going to set the attributes of this thing. Attributes at 0, just like we did in the other, remember, attributes in our shaders. These are attributes. We're setting the attribute position right here, dot, and then buffer index. This will just be 0 because that's what's going in StageIn is buffer 0 right now at least. And then so that equals 0. We're going to put that to 0. We're going to copy this line, copy, and you can just do Command Shift and then left will highlight the entire line if you're curious on how that worked. So we're going to use attribute 0 and we're going to apply the, you can do a description. So it's like, oh, there's a position or something like in string form, but we're not going to do that. We're just going to set the format equal to, well, not 0. We want to do dot. It is a float 3 input, float 4 output. So we're doing a float 3 input so it knows what the hell we're talking about. We're going to paste this guy and we're going to do dot offset 0. Yeah, so the first float 3 size is going to be attribute 0. And now we're going to do the exact same thing, except we're going to do it for color, which is attribute 1. Look at this. So 1, 1, 1. And it's going to be buffer index 0 still, because that's where it is buffer index 0. This is still 0. But it's not a float 3, right? It's a float 4. And the offset is going to have to go after our first part of the data, which was a float 3. So this has to be memory layout size of float 3 dot size. Now, we've told it what each individual thing is. Now we need to tell it what its layout stride is, because this is a vertex layout. We need to tell it what this layout stride is, and that's just as easy as going vertex descriptor dot layouts dot, or at 0 obviously, dot stride equals memory layout of vertex dot stride. So that is how you determine what the hell the vertex descriptor is. We're describing every single little aspect just so it knows how to decipher it, and that'll come in handy a lot in the future. So now we've done this. Now what we need to do is put it into the render pipeline descriptor. See that it isn't, we haven't put it there. We just created it. And so that's one line that says render pipeline descriptor dot vertex descriptor equals vertex descriptor. Now we have our vertex descriptor. Remember how it complained at us? No vertex descriptor was set. Well, and now we have a vertex descriptor. So if we go ahead and press play, this is vertex descriptor is now attached to this render pipeline, which then gets passed in down her, and we should get back our freaking plane. There it is, except now it's a lot more efficient, and we don't need to, it's per vertex, so we don't need to keep track of these stupid little vertex IDs. Freaking awesome. Time, 1 hour. I'm gonna go like 5 more minutes, and we're gonna do some constants because we want to move this freaking thing around. We're gonna move it around. So constants. There are we're gonna go over 2 different types of constants in the next video. We're gonna go over scene constants and model constants. Scene constants is if I were to take this pen, you're the camera, right? So the camera is like kind of represents the scene constants. The camera is looking at this pen. If you want to move the camera, you can't. You can't move the camera. You have control of the model, the pen, but you can't move the camera. So what you can do is utilize the scene space and rotate every object in the scene around the camera. You see, you're not going to move the camera. You're going to move every object in the scene around the camera, around you right now. And so that is the scene constants. The model constant is going to be placing this in space, and there's 3 different things we can do. We can do a transform, which is shifting it in space. It's just a fancy transform it, translate it to over here. It's not transform, translate it over here or up here or down here. There's what's known as rotation. So which way do we want to rotate it around the axis? So this would be like the x-axis. This would be the z-axis, and the y-axis would be like just turning it like this. But anyway, so there's rotation, and then there's also scaling. And what scaling is basically taking this pen, and when you create a model in like Blender or Unity or whatever the hell you make your objects, you create them at the exact same size, and then when you put them onto the computer, you shrink them down so that me and this pen aren't the same size. It fits in my hand. You scale it. We'll go over that probably, again, the same exact words I just said, but in the next episode. But what we want to do is we want to be able to pass these different scene constants and model constants into the GPU so that our vertices can do work on, because that's what the GPU is good at, is math. It's good at doing matrix multiplication and maths like that. So we're just going to kind of prepare for that, and I'm going to show you how the hell we do that, and maybe move it around a little bit, and we will. So in types, we're going to go here, and we're going to create a new thing called constants. Okay, and then we're going to just have one variable called animate by, and that will be a float. Simple as that. Now we have an animate by and our constants. Let's go back out to our renderer, and let's instantiate a constants. So constants equals constants, just like so. And it's going to say it's complaining because we haven't actually said what animate by is. And so if we instantiate it inside of our types equals 0.0, it won't freak out. It won't freak out at all. Okay, so now constants is 0.0, and it's just data. One thing I'd also like to mention in a second. All right, so now that we have our constants, we need to put it inside of a vertex buffer. If we want to send it to the freaking guy, we have to send it to if we want to send it to the device, to the GPU, we need to send it in a vertex buffer or in a MTL buffer. And so we're going to do that right here. And so our bytes we're going to go right here. Wait, no, sorry, thinking wrong, something else. Sorry, the MTL buffer is used for anything over 4 kilobytes. So if your data is over 4 kilobytes, which is a lot of freaking data, it's kind of a lot of data. But like if you do a couple of matrices, a couple of float constants, a float's only 16 bits. It's not 4 kilobytes of data. you're fine. And so what we're going to do is we're going to send it over as reference rather than inside this huge buffer. And so all you have to do is you can skip this build buffers, but down here we're going to go command encoder dot set vertex, not buffer, but bytes. We have bytes, and we can set the bytes of the reference to our constants. The length is going to be memory layout, and since we only have one, we can just go constants dot stride, and then we're going to put this at 1, not buffer 0, because we already used that. We're going to put it at 1. So boom. We might actually be able to use 0 still. I don't think it's 0, 0, but no, I'm putting it at 0 right there. StageIn, sorry, done. So we're going to put the bytes at 1. Now that's easy. That was simple. Let's go to our shaders, talk about how we do that. So now it's at buffer 1. Well, this is going to be what we need something to represent it. So we're going to take in a struct constants. We need to represent it on both sides. We're going to do a float animate by. Okay, and then we're going to take in the constants, and you can take it in as a, and we're going to make this const because this won't change. We're going to make this a constant because anything that comes in as a reference, you're going to want to make a constant, not a constant. Const has to do with like device space, I think. There's a difference between these two. Sorry, I don't know it off the top of my head. I think it has to do with where the space is, but we're going to take in constants, and then we're going to take in a reference to constants, and that will be at buffer 1, like we said. So now we have our constant constants, right? And then that has animate by, so that comes in. Right now it's set to 0, and then what we're going to do is press play, just make sure everything's kind of functioning. The bytes are aligned correctly, and we still get our beautiful freaking square. Oh boy, here we go. Yeah, what are you talking about, dude? Because I can't spell things. You know, I college grad, don't know how to spell anything. All right, doesn't make any sense. All right, so we have our constants. Nothing breaks, right? So now our constants are on the GPU, but they're set to 0. I'd like to point out that if I were to go into my types right now, set this to 0.5, what do you think is going to happen? Oh, wait, no, we're not updating anything. If I set the animate by to float 0.5, and I go into our shaders.metal, and I say something like vout.position.x plus equals constants dot, well, we have animate by. What do you think is going to happen? So I'm going to plus equal animate by. See what happens. The x coordinates, so we got that. It's going to fly off the screen? No, it's not. It's going to go over by half, and it looks like exactly half the screen. And why isn't it? We're doing plus equals. Why the hell would it not just fly off the screen? That's because we're not updating animate by, and it's going back to 0 every single time. Per vertex going back to 0 every single time, then it's adding the animate by again. So we have to update this animate by to go higher. And so in our renderer, what we can do is right here, before we actually set the bytes, we can do something like let delta time. We'll get the time in relation to what we're rendering. So there's a good way to do this. We can just go float view dot current dot preferred, sorry, frames per second. And what that's going to give is us is 60 right now. We can set it to 120, but it's going to give us 60, and then we can say constants. Oh my goodness, constants dot animate by. We're just going to update that by 1/60 every single frame. That will do something kind of bad. That will make it shoot right off the screen. And so if we wrap it in something like a wave, which goes positive one and negative one, like cosine, it won't actually go off the screen. It'll just kind of go side by side by side because it's X. It's going to go across the X axis. And you see we have movement. Oh, it's a moving box. All right. And so you can do like cool stuff with that. Like there's a, like I said, you can do like X, Y right here. And then we'll kind of see what that looks like. I'm going to check time. Yep, we got to get off. It's getting late. It's 10:30. See, now we have like, you can do that. Pretty soon this will be matrix multiplication. You can do stuff like, so we'll do that, but then we're going to go right here and we're going to go boom, and then we're going to make it like the sign. So we're going to make it go in the opposite thing. And then we'll just do like the Y variable instead. And this way, like this is how you animate. You basically pass in the constant and then you multiply it by whatever scene constant or model constant, and we'll update this and manipulate it and do really cool things. And so, yeah. Sound cool? Sounds cool to me. I mean, we can even do this. Times vout.position.y. Let's see what that does. Since it's going to go from 0 to 1, let's see what happens. It should give us some, yeah, you see? So as it goes, it's going to go negative, and then it's going to go positive again, and then it's going to go negative. And so, like, there's a lot of cool little things we can do with that. And so I'm just going to leave it at that. I'm going to go down to my GitHub. Now that we have constants going through, I'm going to let that run. And then I'm going to go here and just check in. We have we have constants / vertex rendering. I'm going to commit that. All right, I'll sync it. And I'll publish it, and then you guys can get that whenever the hell you want. And cool. I will see you when I see you.